accountant, and he diagnosed him with the voyager syndrome. And when the accountant says, "What's that?" He said, "Well, in your very busy schedule, when you try to pause between tasks, you will just blank out." So anyway, some people had the hindsight. Last fall, Tim sent me a 15C plus and said, "Hey, play with it and see how fast the integrate works. It's about 100 times faster." And he was right, it was blinding fast. And after a few months, I decided to test the speed because my initial impression was that every operation was sped up by the same proportion. Of course, that was wrong. And I approached Richard as the announcement of the limited edition was near. I said, "We can do an article on hpcalc." He said, "Sure, yes we can." So I tested the article by running a set of programs. Usually I have one short program that initializes the test, and like in label A, and then I would use label B to run the program. Each test uses a program that repeats a set of operations for a fixed number of times. I did not use Gene's approach where I would crank out an open loop for a minute or whatever and then see how far it goes. I used simple programs to execute empty loops, and that was sort of my baseline offset. Empty loops, and also sometimes I had loops that had a recall operation, 1 or 2 recalls, because that would feed, as I will explain later on, arguments for functions and operators. My goal was to see what the speed ratio between the limited edition and the vintage version. And of course, to streamline dealing with arguments, rather than feeding the values in the test, I had the label A that initializes them, that store the value in memory register, and then during the test, recall them from memory register. This way, all the operations had the same speed as far as accessing the 1 or 2 arguments that they needed. Since the 2 machines differ significantly in speed, I use different number of iterations. In this way, the test would be reasonable and accurate. My error was between 0.1 and 0.2 seconds using a 41CX built-in timer. So I did not want to make the test too short where the error becomes significant, or too long. I would miss it so many times and it would be very frustrating. I recorded the voltage of the batteries used because apparently that was important, and the ambient temperatures in which I carried the tests. The test code, here's an example. The first one is just the empty loop. Label B. I used the decrement and skip if equal to count down because I had a wider range. If I used the ISG, I would be limited between 0 and 999. With the DSE, if I needed a higher range, I could do that. So that was a good option to go with. Second example is also a loop that times the recall from register. I use register 9 and 8 to put arguments. So that was also a way to measure the speed of the recall operation itself. And then the time for that loop I used as an offset to measure when I use single functions, which you will see in the third example. Here we have, I'm testing the sign, label A, I store 0.6 in register 9, put 100 in the register 0, which I use as the test loop counter, switch to radian mode, just because I like to, and then label B, I recall my 0.6 repeatedly, execute the sign, and then of course do the DSE and continue the loop. And I subtract the time from this loop from the other one to get the impact of the sign. Now here, I registered the data as operation sets because most of the operations, with the exception of a simple store, will influence the stack and or the last X register. So you're really not doing just one thing, you're doing a lot of things. Only the store would simply copy the contents of the X register, the memory, and not influence the last X register or the stack. So.
May I ask a question, Namir?
Yes.
Can you take back, please?
How do you do that? Back.
Back arrow.
Oh, yes.
One more. There you go.
Okay, you have the initialization code there for the third example. If you put this in front of label B, it might affect execution times.
Because the go to B.
Because the label search might be affected.
There's a 15C.
Having the label A code in memory might affect execution time, even if it's not executed more than once.
Does the 15C cache the offset?
No, no, it does not.
No.
It doesn't, huh? Good point.
So alone having some more code in the memory might affect execution times.
The runtime of a go-to is not constant.
The go-to would have to start at A and go down to try to find B each time is what the...
Oh, okay, I see what you're saying.
That's the
I
same
don't know
for
what
the
the
machine.
15C.
Yeah, it's the same in both machines, yeah.
That's true.
Yeah. Yes. Here's the example where we have operations that use multiple arguments, y to the x. I use recall 8 and 9 to supply it with arguments. The second example is using solve, and the two guesses are, again, in registers 8 and 9. Third one is testing the integrate. Again, the limits of the integral are in 8 and 9. The last example is special, because I love statistics. It's testing the statistical summation operation. Here, the test is I'm looping, and each loop has another loop that adds 100 pairs of random numbers, one for x and one for y, and then do the sigma plus. So, and then in addition, I did some special tests, longer programs, calculating e to the pi using Taylor expansion polynomials. And it would add each term until, if I round that term according to the current display, it becomes 0, then I stop, and then display the result. That was one. Using the integral command, calculating the integral of 1 over x from 1 to 100, and that's, of course, the natural log of 100. And the third one was calculating the root of my favorite function, e to the x minus 3x squared between 3 and 4. The last one, Richard had suggested using Joe Horns' program to converting decimals to fraction. And the article mentions a specific version, because I think Joe kept changing it, and to avoid confusing people, I said, here's what I'm using. So the article has that specific version. Results. The store and recall, I kind of grouped the results not by, by similar operations. The store and recall operations show the highest gain speed ratio about 180. That's kind of maxing out there. The stack roll down operation, in my mind, I'm dividing it sort of like around 150, 120 to 150 is moderate, 150 and above is high, and a lot of operations I will see hover around between 110 and 100. So the stack roll down, I did complete stack roll down, although it doesn't matter because I'm really repeating the same operation, is 166. Addition and subtraction showed the gain ratio of 154, so that would be in the higher sphere of gain. But multiplication and division operators had a speed ratio of 110. That 110 is like a magical number. A lot of functions have a speed ratio gain around that number. And in fact, when you look at the set below, the square root, square, reciprocal, and raising to power have speed ratio that average 114. So that 110 magical number, we see it again. Again, the trig functions and the inverses have speed ratios that average 111. So again, that seems to be the gain that has the most weight. Hyperbolic function and the inverses are slow. They drop just above 100 at 102. And so that's among the slowest gains. When I did the converting to polar coordinates was moderate, 122. But the reverse was 102, dropping down to the lower limit of the gains of the LE machine. The hours and hours, minute, second conversions showed some impressive results, 152. That was pretty good because I'm saying that the 150 is the limit above which I say this is an impressive gain. Common log, natural log, and their inverses, again, have a speed ratio gain of 113. Again, we're near that 110 magical limit. And as is the random number generator, has a speed of 113. The integer and fraction functions actually did very well. They have a speed ratio average 162, so that's above the 150, so that's in the highest speed, yes.
Quick question. When you say average, do you mean you ran the exact same test?
No,
many
I'm
times?
looking at the results, the speed ratios, and I'm saying, well, they're kind of average because they're similar operations.
But average over a bunch of different examples or average over the same example repeated?
Same example.
So you ran
Between-
the same test and the same
I
test?
have like one test for the fraction, one test for the integer, and I look at the result because they're similar functions. I'm kind of grouping.
But you did more than one trial of a given function.
What I'm getting at is if you do a single test and you time it,
Yeah.
and you run the same test again, you run it 10 times, is there much of a distribution?
No, very small variation.
Very, very small.
Yeah, I mean, because usually when I do the first two tests, I'm really zooming in on when it actually stops. And it's the third or fourth reading when I'm beginning to get to the 0.1, 0.2 error in my speed. The integral and solve functions actually did rather well. 124, that's they're above 110, so I call them a moderate gain. And due to the complexity, that's a good accomplishment. Now, adding the random number of pairs of x and y gave a gain of 115, and I think that was disappointed by the fact that they were using the random number generators twice in each loop, and those were I think it slowed down the whole process. But if you compare it to calculating e to the pi, the ratio gain is 154. And in fact, Joe Horns' program is even more impressive. The gain is 162. And as I look at the code of these two, they happen to be using functions in which the limited edition has gained enough speed to make the entire program go faster. While the statistical summation test was using the random number that kind of slowed it down, so it slowed down the whole thing. It was like a bottleneck. And that's it. Okay.
Question? The slowest and most horrific of all possible operations you can program is placing let's say, to place on the stack a 10-digit number, a 10-digit negative number with a 3-digit negative exponent. Did you ever try anything like that?
Doesn't do
Because-
3-digit exponents.
Something very, very slow has been going on. This goes all the way back to the days of the HP 67. And apparently, when we put numerical constants in our programs, they're not compiled or anything. They're just taken apart one digit at a time, and the length of time it takes to execute that is very long. And it seems to be related to the number of digits that the machine has to
And
process.
that's why I would pre-store the constants and just feed them as we go. So I have
fast, always pre-store your constant.
yes.
Which leads to another thing, a request to HP. If you have a numerical constant library, like in 35S, we have all these physical constants. You know, a few other commonly used numerical constants, like 1 over the square root of pi, or 1 over the square root of 2 pi. How about plus or minus 1, plus or minus a half, and plus or minus 2 would be incredibly useful and would speed up programs tremendously if they could be in that constant library.
Yes.
Yeah, I have two questions. First, do you know what the clock speeds are of the two calculators, and see how that about 110 or 120, if that matches? And the second question: Has anyone compared the new 15C with the 50G for doing things like solve or integrate or solving an 8x8 system of equations?
No, I mean, the first one, HP can tell you the clock speeds. The second one, no, we were just comparing between the old and the new.
Cyril has his hand up.
Because this way I can use exactly the same code. Otherwise, well, if you say if you write it in RPL, I didn't write it as efficiently, then there's more factors. Yes, sir.
Do you have any clue why some of the operations are 150, 160 times faster, while some of them are only 110 times faster?
No. I thought everything would have sped up by the same. That's why I was a bit surprised that some operation really gained and some, I mean, everything is above 100. So when the commercial came out, like I said, Richard, why did he say up to 100? It's like at least 100, but of course you have to specify the upper limit, you know. You can't say, yeah.
I was just wondering, did you ever compare the 15C plus to the LE to see if there was any real difference?
It was a 15C plus, but I had updated the ROM, the firmware to the current release.
Oh, I
Yeah,
see.
I had the beta, but yeah, Tim said, please make sure you have the latest. That's what we went for. Yes,
Maybe I
Max.
have an answer to Cyril. You're emulating a processor. The hardware processor has a fixed clock speed. So it does its operations, its complex operations, in a certain manner of clock cycles. You have to emulate those operations on another processor, which has a totally different speed. So it's not just faster, but it takes different times for each execution, low-level execution of another processor it executes. So just adding two BCD numbers might be faster on the original hardware than on the emulation, or having a store or recall might be faster on the, or might take a similar time on the processor than adding two numbers.
Let me ask you a question. Do you honestly believe that I did not know the answer to my own question when I asked this?
So what you said. All right, give us the answer.
I know the answer is very simple. During the emulation process, most of the instructions map relatively cleanly to a very small amount of C code, except in the case of BCD addition and subtraction, where something that was a very simple single operation on the original CPU has to be done with a much more complicated routine to do the BCD add and sub. And definitely when you look at the timing here, it brings the difference between everything which includes BCD code and the stuff that does not.
Okay.
And that's really what causes the difference here.
Very interesting.
And I was just going to say, Namir, the up to 100, that took about 3 months to finally ram through legal. It was ridiculous. They wanted all sorts of stuff and insisted we couldn't say it, and it was very difficult. How do we prove this, and blah, blah, blah. So, originally I said up to 180, which, you showed there, but they wanted me to demonstrate and show to them how it worked and how to do all these timings, and I'm like, I'm not wasting my time trying to educate lawyers how to use this. So, I just said, okay, up to 100, and they seemed okay with that. So.
If I could ask Cyril, do you know how much of that performance difference can be attributed to going to the word at a time BCD arithmetic that I suggested to you versus the digit at a time?
No, I don't. I could very easily make a ROM with a different version of the code and we could try it.
That would be interesting.
That'd be interesting. I don't think it's gonna be that huge because even in something that has a lot of BCD arithmetic, such an addition, as you know, the algorithm has actually very little BCD arithmetic in it. Most of it is just jumps and stuff like that, which doesn't get that influenced by it. So I don't think it would be very significant, but it might give a little bit of a difference.
I just want to make a point about loading the constants. In the RPL machine, the constants are built in. So if you do, 1 through 100, and I'm sure there are others, those get loaded instantly.
All right, let me run through this real
And even
quick.
if they're not built-in constants, they are compiled in.